And then, of course, for decades, we've been studying large samples of galaxies in the present-day universe. But trying to put together a longitudinal understanding of galaxy formation from these different cross-sections is like trying to understand human development if all you had were records and pictures of children in the 1900s, teenagers in the 1920s, and mature adults today, right? So there are things that you can learn, but it's not necessarily straightforward. And you need to find things that will allow you to link populations across time. And so if the question is, what are the physics that drive galaxy growth? We need to do two things as a field. We need to study individual galaxies in detail at different times, and we need to be able to connect them across cosmic history, right? And we can do both of these things observationally and theoretically, and I would argue we can do them best when we combine both of those things. But what I want to talk about specifically today is how we can use galaxy chemistry as one of the things that allow us to not only study individual galaxies at a specific time, but also connect galaxies across cosmic history, which is something I also chatted a little bit about with folks at coffee this morning. Okay, so 3 parts to the talk. First, I'll review how we use chemistry as a probe of galaxy assembly. I'll talk about the results from my JWST program, Cecilia, and specifically the metallicity and abundance patterns we're learning about in galaxies 10 to 12 billion years ago. And then I'll finish with a potpourri of things that I spend a lot of time thinking about, and that we're still trying to figure out how best to interpret some of these puzzling observations. And maybe you'll find something that is of interest to you as well. Okay, so galaxies are the engine by which the universe goes from being a relatively homogeneous soup of hydrogen and helium, and then through star formation in galaxies, we end up with still a lot of hydrogen, helium, but now trace amounts of heavier elements like oxygen, iron, carbon, etc. And if you remember from your, I guess I don't even know what class this would be, but your graduate coursework or undergraduate coursework, if we write down the mass fraction of hydrogen, this is something we refer to as X, the mass fraction of helium as Y, and the mass fraction of literally everything else as Z, which is a bucket of elements that we refer to as metals, regardless of whether or not a chemist would agree that they are a metal. But that's why you'll sometimes hear people talk, about metallicity, you'll see Z, but they could be talking about any one of those elements. So one of the most fundamental observations comes from looking at the amount of heavy elements in galaxies as a function of their stellar mass. And so here I said metallicity could refer to anything. In the case of star-forming galaxies, we're usually looking at the amount of oxygen in their ionized gas. And what I'm going to show you are the results from Tremonti et al. 2004, which is without a doubt one of the most highly cited modern astronomy papers, and really set the stage for us thinking about what it means when we look at this monotonic correlation between the amount of oxygen in galaxies and their stellar mass. But the most intriguing thing, perhaps, is that if you compare this to what you might naively predict simply from tracking the amount of metals formed in stars, the amount of oxygen formed in stars, and the depletion of gas through star formation, you don't get the right answer, or you don't reproduce what we see. Instead, you need outflows to be driving some of that oxygen that's produced in stars entirely out of the galaxy. So this steeper slope at low masses is one of the ways in which we can track the flow of gas in and out of galaxies, which is really exceptionally difficult to do because much of that gas is not otherwise sort of emitting. But the things that we learn from this kind of analysis are that lower mass galaxies are losing preferentially more of their oxygen compared to high mass galaxies. And this is interpreted as being because their shallower gravitational potential wells make the feedback from exploding massive stars, etc., more efficient. But there are a lot of other elements that you can look at. You see similar behavior if you look at some of the other easily measured elements or comparatively easily measured elements like iron. But what I want to draw your attention to now is the value that you derive from measuring the amount of more than one element at a time. So I'll start with oxygen and iron. Oxygen is formed on short time scales in core collapse supernovae, basically instantaneously in terms of a galaxy's lifetime. In contrast, iron, some of it is also formed in those core collapse supernovae, but the majority of iron in the solar neighborhood is actually been produced on a longer time scale thanks to type 1a supernovae, right? So they're being formed through the lives and deaths of lower mass stars. And so if we follow a galaxy through its lifetime in the space defined by these two elements, so here we have the amount of oxygen relative to iron on the y-axis and the amount of iron or oxygen, basically some total metallicity on the x-axis. And that point is a galaxy. At early times, its enrichment is going to be determined by core collapse supernova yield. But once type 1a supernovae begin to contribute to the ISM enrichment, you'll see a rapid decline in oxygen to iron as the iron production from type 1a begins to swamp the signal, essentially, from core collapse supernovae. And the details of what happens afterwards depend on the importance of recent star formation, the stuff producing a lot of oxygen and a little iron, versus star formation with some time delay. Basically, now the low mass star is contributing iron to the ISM. If you have a galaxy that forms stars more quickly early in its life, it can reach a higher total metallicity before type 1a supernovae have a chance to contribute. So the path a galaxy takes through this space depends sensitively on its star formation history. And so for those of you who are familiar with galactic archaeology or near-field cosmology, you're probably familiar with this kind of diagram. And indeed, it's been used to great effect for many years to study the star formation histories of nearby galaxies, where we can resolve individual stars, and especially things like our own Milky Way. So if we look at the abundances of halo, bulge, and thick disk stars, so the oldest parts of our galaxy, we see that on average, they tend to be rather high in oxygen to iron, or you might be more used to seeing this labeled as alpha to iron, whereas stars in the thin disk are really on this decline. They were formed after type 1a supernovae had started contributing significantly to the Milky Way enrichment, and the sun is somewhere down here. And so keep this in mind, because we're going to come back to the mass metallicity relation and the Wallerstein-Tinsley diagram throughout the talk. Any questions about any of that?
I have a question.
Yeah.
So there is a not small scatter between the mass metallicity relation. Can we attribute the outflows as a reason for the scatter?
The scatter in the mass metallicity relation has been a subject of much debate since the Tremonti et al. Paper. Some of it may be due to sort of the efficiency of outflows, but it is also correlated in the local universe with other properties like star formation rate, right? So you have two values on the y-axis. You have the oxygen that's formed in stars, and you have the hydrogen that's basically in the total gas reservoir. So this oxygen is being formed in stars and can be ejected by outflows, but you can also have inflows, you can have other things that essentially cause the balance between these to change. And so the idea that we see at fixed stellar mass, something with a higher star formation rate and higher gas mass have lower oxygen abundance, is usually, this is something called the fundamental metallicity relation. Has more to do with the regulation of the total gas reservoir, we think, as opposed to only a signature of outflows. Sorry, it's not a very clean answer, but it's not a very clean observational signature. Does that help?
Yes.
Okay. Oops. Okay. So, oh goodness. There we go. In order to continue, I need to tell you how, no, okay. Sorry, it's a little laggy. Why we don't want to only look at the nearby universe where we can study things in detail. And the reason why is that we know from studies of the cosmic star formation rate density that over half of all stars in the universe today were formed before a redshift of 1. And the majority of those were formed in this broad peak between redshifts 1 and 3. This coincides with also the peak of quasar number density. So this is often referred to as cosmic noon, when you see both star formation and black hole accretion reach their cosmic peaks. And so if we want to understand what sets the scaling relations in the stellar populations we see today, it behooves us to look back in time at the point when a very large fraction of those stars were formed. And so if we go back to our little schematic here, this turns out to be here, right? So we've done the assembly in the epoch of ionization, but now this is where a lot of differentiation in the galaxy population is going to happen. All right. So the signatures that we use in galaxies out to the largest cosmological distances are the bright emission lines coming from the photoionization heated gas around massive stars in star-forming regions. And so the reason I'm showing you a spectrum from 1987 is to demonstrate that this is a toolkit that we've had for a very long time, one that we have really rigorously tested in the local universe, and which is really built on our understanding of atomic physics. So if we look at these features, there's a lot that you can essentially read off of the spectrum. So the amount of emission in hydrogen recombination lines is essentially counting the number of H-ionizing photons produced by massive stars, so we can derive a star formation rate. If you look at emission in the same element, the different ionization states, you can get a sense of basically how highly ionized the gas is, which is going to be, again, related to the ionizing photon production from massive stars. If you look at the same ion, two lines that have very similar excitation energies but different critical densities, then you can directly determine the electron density. And then most salient for this talk, same ion, but now very different excitation potentials. And if you measure the relative amount of emission in those two lines, you're going to be able to determine the temperature of the electron gas. And so how this works, if we, again, borrow from our textbooks, so this is a level diagram for doubly ionized oxygen, and you have essentially your lowest energy level, your first excited state, and then your second excited state. And these lines, these are the bright ones that you saw in the spectrum before. We call these nebular lines. And then anything that comes from a higher energy level, we refer to as an aurora line. And I'm not telling you this because it's important or that it has any physical meaning. I'm telling you this because I will say aurora line, it will just fall out of my mouth, and I want you to know what it is I'm referring to. Okay, but if you are measuring the amount of emission in a nebular line versus an aurora line, what you're essentially getting is the relative amount of level populations from a higher energy level and a lower energy level, which means that you can determine the temperature because the population of these energy levels will be determined by something like the Boltzmann factor. Once you have the temperature, you can combine this with the other oxygen lines and hydrogen recombination lines to essentially count the number of ions that are needed to produce the emission that you've seen. So this is the way in which electron temperature is really sort of fundamentally related to the enrichment of the gas. So the oxygen is the third most abundant element in the universe. It's very comparatively prevalent in H2 regions, and so it's providing a lot of the cooling. So this relationship between temperature and metallicity is one that's very sort of fundamental. The problem is, because this sounds great, right? You know what you're doing. How often does that happen? These aurora lines are very, very faint because it takes high temperatures to populate those higher energy levels. And so unfortunately, this direct method is often unavailable to us. So instead, people take this direct electron temperature-based oxygen abundance and they combine it with more common observables. So in this case, it's a ratio of 4 strong emission lines, doubly ionized oxygen, 2 hydrogen recombination lines, and singly ionized nitrogen. And you see that there's actually a pretty strong correspondence. And so the idea is that you would, instead of doing the thing that's hard to measure, you would take a thing that's easy to measure, read off the thing that's hard to measure, and go about your day. You can do this for much larger samples, and it's a lot cheaper. The problem is, the scatter around this relation is correlated with other physical properties. So if you're to the right of the line, this is generally going to correspond to higher ionization gas. If you're to the left of the line, this is going to correspond to gas that has more nitrogen at fixed oxygen abundance. And so what this means is that these methods are implicitly assuming that the sample that you use to calibrate your diagnostic have the same abundance patterns, the same gas conditions, and the same mass of stars, the same heating as the sample that you want to study. And this is not generically true, and this is certainly not true as you go from star-forming galaxies in the local universe to star-forming galaxies in the early universe. But fundamentally what this means is that there is no strong line calibration, which is what these are called, that's universally applicable. So you have to be very careful when you are choosing this, or if you are a theorist looking at papers where people have chosen this, recognize that that choice is important. Okay, the other challenge as you move to the high redshift universe is that by redshift 1, a very significant fraction of the rest optical spectrum is now in the infrared. And by redshift 2, basically every line that we've carefully studied over the last 30 years from the ground, 40 years from the ground, is now in the infrared. And it was only in the last 10 years that we were finally able to build up large samples of rest optical spectra of high redshift galaxies. Predating Webb, 10 years ago we were using the next generation of multi-object near-infrared spectrographs and ground-based telescopes to learn a lot. And of course now Webb is really just cleaning up. But prior to Webb, all of us working on this spent hours and hours, days and days, or nights and nights on Keck, trying to basically wring as much blood from the stone as we could. And we did actually learn a lot. So this is a sort of nice, clean summary figure from a paper by Ryan Sanders showing that at fixed stellar metallicity, we see this increasing or decreasing amount of oxygen in galaxies, which in, analogous to the decrease in metallicity at lower stellar masses is related to potentially higher gas fractions or more efficient outflows. And then one thing that I think is really cool that came out a little bit later was if we look at the massive stars in the same star-forming regions at high redshifts that are illuminating the gas, right? So we've spent some time talking about these emission lines. If we look at the massive stars that are doing that photoionization, we can directly see their photospheres and measure their iron abundance the way that you would measure the iron abundance from a star in the local universe. And so when you combine what you know about the oxygen abundance from the gas and the iron abundance from the stars that are heating the gas, what you find is that high redshift galaxies have to have high oxygen to iron ratios. And so what bell is that ringing in your head? One of the students, sorry, I'm looking at the 2 students I met at lunch. It means that these galaxies are all young enough that type 1a supernovae have not contributed significantly to their enrichment. They are young, despite being relatively massive. This is a few times 10 to the 10, almost up to 10 to the 11 solar masses in some cases. So this tells us something about their evolutionary state. But the problem is this is all based on, this is a 300 object hour spectrum. This is a composite spectrum. This is maybe 60. And you can still see that we're not seeing like the aurora line. Yeah, it's not even here because we didn't see it in the stack. So the kinds of detailed astrophysics that we can do with local galaxies, we still were not able to do with high redshift galaxies. And this is where JWST enters. So something that we've been trying to do for 10 years from the ground, my co-PI and I, Gwen Rudy, from Carnegie Observatories in Pasadena, we proposed to do this with Webb. We proposed to go and take very deep rest optical spectra of redshift 2 to 3 galaxies so we could measure their aurora lines, electron temperatures, and direct method metallicities using the method that I just told you about. So we took 30-hour spectra of individual galaxies, which might not sound as incredible today, but at the time blew our minds. We were like, we're gonna sit on the same galaxies for over a day. And then it's yielded some really remarkable results. So Cecilia is based in one of the fields of the Keck baryonic structure survey, for those of you who are cosmic moon aficionados. These are rest UV color selected galaxies that have very rich ancillary spectra in the rest UV and rest optical from Keck, and quite a lot of imaging. The galaxies were prioritized based on predicted aurora line strengths, based on sort of detailed analysis of the spectra that we had in hand, as well as practical aspects that would ensure that for a sort of given distribution of stellar mass and star formation rate, we had a better chance of detecting the emission line. The team is relatively small, I would say, by JWST standards, but we're doing a lot of really good work. So Gwen is my co-PI, Ryan Trainer, who's a professor at Franklin and Marshall, is the other senior person on the project, and then we have this really wonderful group of junior people. Noah Rogers is a Sierra Fellow at Northwestern. Caroline and Natalie are graduate students working with me, and Manelis is actually an undergrad at Franklin and Marshall who is applying for grad school this year. So if you happen to be someone who will be sitting on an admissions committee or a fellowship committee, please keep an eye out for his application. Okay, so you saw the one example of the stacked spectrum, and which was like 60 hours, I think I said. This is 30 hours with Webb on an individual spectrum. And not only do you see all of the strong lines, right? So this is H alpha, this is N2. Actually, basically none of these other lines were in that spectrum because JWST lets us go deeper and to redder wavelengths. And so these two boxes highlight the location of these aurora lines, which had not been detected in large or representative samples of these redshifts prior to Webb's launch. And to me, it's really remarkable that you can actually see them in the 2D spectrum, which is something that I didn't expect at all, but was very helpful because the data reduction took a very long time, but we knew that they were there because we had at least first looks at the 2D spectrum. So Noah Rogers has really been leading this. He's our MVP. And what we have found is that based on our selection and our very deep approach, which was deeper than the other Cycle 1 programs with similar scientific goals, we're able to go to relatively low electron temperatures, which means that we're going to a region of parameter space that would basically always be inaccessible from the ground. The only things that we had from the ground typically were higher electron temperatures because it meant that it was easier to populate that higher energy level and have a stronger auroral line flux. So what you should be looking at are the yellow symbols, which are Cecilia measurements based off of a detection of one of these auroral lines. And you'll see that we are skewed to one side of the distribution, the one that's harder to measure. And the ones that have been either from shallower programs or more serendipitous detections are the ones at higher temperatures. And so Cecilia plays a really critical role in making sure that we're filling out this parameter space and able to study a truly representative sample of galaxies at these redshifts. Okay, but what's the major punchline here? So once we have the temperature, we can measure the direct method metallicities, or the direct method abundances, And we can do this not only for oxygen, but for other elements that we see emission lines of in the spectrum. And what I'm showing you here is sulfur to oxygen on the left and argon to oxygen on the right as a function of oxygen abundance. So in a way, this is kind of like the Wallerstein-Tinsley diagram, just kind of rejiggered a little bit. The gray diamonds are local metal-rich H2 regions, and the blue squares are local metal-poor galaxies. And you see that the high redshift sample, the Cecilia sample, which are the orange and yellow circles, yes, large error bars, large scatter, but on average, significantly offset to lower sulfur to oxygen and lower argon to oxygen, whereas the local samples basically fall bang on what we see in the sun, maybe a little bit low in sulfur to oxygen for the emission line galaxies. And so, honestly, I wasn't sure how to interpret this immediately. This is something that we first saw in Noah's first paper, which was based on a single redshift 3 object that then sort of led the way for other people to start measuring these abundance ratios. But the other thing I want to draw your attention to is the dot dash orange line, which is the average for Cecilia, and its close correspondence to the dotted black line, which is the core collapse yield for sulfur to oxygen and argon to oxygen. So now we're not just trying to cobble together evidence of alpha enhancement from measuring different parts of galaxies, the stars and the gas, using indirect methods. Here we have direct, conclusive proof that these galaxies are chemically immature and enriched almost entirely by core collapse supernovae, even out to relatively high metallicity. So in some ways you would call these chemically mature, but we know that they're young. They can't be old, otherwise we would not see this subsolar sulfur to oxygen and argon to oxygen. So let's go back to Jennifer Johnson's lovely periodic table. We looked at oxygen and iron before. What about sulfur and argon? They're just like iron. Some sulfur and argon are produced in core collapse supernovae, but a non-negligible fraction in the solar neighborhood comes also from type 1a supernovae. So just like iron, sulfur and argon are able to trace core collapse, or to help us trace core collapse supernovae versus type 1a enrichment. And what's really great about this is measuring iron is very, very hard. Because it has to be done from the ground. It takes basically 20 hours per galaxy from the ground to do. And sometimes, if you wanted to do this for supernova host galaxies, this is something I've been thinking about, this is like 2 nights on Keck for a single object. That's wild. And so this was really cool, and it is supported by studies that have looked at the behavior of these ratios in M31, where they're also trying to understand some peculiar behavior in the star formation history. So this is really exciting to me, and we have the largest sample sort of demonstrating this. Okay, I'm going to move on to a slightly different metallicity topic. Any questions on the core collapse enrichment? Okay.
What mass of these galaxies?
Yeah, so they range between 10 to the 9 and several times 10 to the 10. Solar masses.
So we discussed this briefly earlier, but supernovas should blow stuff out of the galaxies.
Yeah.
You still see the gases just from supernovas, so to speak, or at least the metals, just from core collapse. What's the mass loading factor? Can you get it very well? And how does it depend on the mass?
Yes, so Norman's referring to another paper that I showed him this morning that I'm not going to talk about here.
That's what I mean.
So some of the Cecilia galaxies are in the sample that I showed you. And so the mass loading factor, oh gosh, I don't have it right off the top of my head. But I see, okay. So one of the things to keep in mind is there's some belief and evidence for the fact that you could also get some kind of disequilibrium in the abundance patterns because you might preferentially blow out enriched gas near core collapse supernovae versus the type 1a enriched gas. I think the fact that I think that would go in the opposite direction. So I think if anything, we would maybe see things that looked too, if you retained the type 1a and ejected the core collapse supernova, you wouldn't get this signature. Anything else? Yeah.
So you talked about like the scatter that you observed. I'm curious, like, do you have any idea as to like if, let's say, like a few galaxies are closer to each other, sort of like, do their environments make them have like more likely to have similar properties than, let's say, like a cluster of galaxies like somewhere?
Yeah, that's a really great question. Obviously, we do see correspondence between galaxy properties and environment in the local universe. This has been much harder to diagnose at high redshift because these fields are really small. And also, like, the total survey area for all of KVSS, which is like hundreds of nights on Keck, is 0.24 square degrees. And so I think this is exactly the next frontier. So things like Rubin will allow you to do sort of selection of galaxies at a variety of environments because you can get a good, reasonable photo-Z, and then you have to embark on an ambitious spectroscopic follow-up campaign, but we'll be able to answer your question. I think you might also be able to start learning some about this from things like DESI or PFS, the prime focus spectrograph on Subaru, or MOONS, which is another fiber-fed spectrograph going on VLT. So I think this is basically what's coming up in the next 5 to 10 years.
Related to the agreement with the core collapse supernova yield, does the agreement change if you change assumptions of the IMF or the multiplicities that is generating those yields?
Yeah, so certainly those yields depend on both of those quantities. I think in this case, we actually did pull core collapse yields from a metal core a yield table. I don't know, we did not test different IMFs. So I don't have a great answer off the top of my head for how big of a difference that would cause. But because these elements are formed in different amounts depending on temperature, right? They're temperature sensitive nucleosynthetic pathways, you can actually get a difference. I just don't remember how sensitive argon to oxygen and sulfur to oxygen are essentially to that.
Yeah, I was also thinking of the multiplicity. If you have binaries and they strip
like
material,
products? Oh, you mean just stripping?
Or closed binaries where like you can strip material one from the other, like material that goes out.
Yeah, that's a really good question, and not one that we've thought a ton about. But yeah, that's something.
Because it would be good to provide constraints for those things.
Yeah. Well, and we can talk about this tomorrow. There are other probes of strip stars in these galaxies that you could imagine putting together. Okay. All right. So this is all what you can do, for these individual galaxies. But I said that one of the goals is maybe to have a new recalibration so that you could learn about the enrichment of larger samples without the same worries of your calibration sample being different from the sample that you want to learn about. And so I'm showing 2 examples, actually from the 2 other Cycle 1 programs that have done this exercise with their samples. And you can see we're really building up sample sizes. So they've basically done a kind of superset analysis. So this is their galaxies plus every other detection in the archive. And, pretty good, right? You do see the fact that you can draw a line through these samples. But I'm going to do something so that you can see that we're still kind of in a problematic place, which is the x-axis now, or the y-axis on the previous plot, is what we're measuring. And the y-axis is what we want to derive. But you'll notice now that a lot of these lines look vertical. So that's not great. Maybe if you have a metal-rich galaxy, you're okay. Or some of these like combined things, but even so, this is O2. I would argue that we still are not necessarily in a place where these are actually going to be super helpful, because a lot of the galaxies at these redshifts have spectra that just aren't responding very sensitively to metallicity in only a handful of lines. And none of this says anything about the correlation, about the scatter around these relations with other properties. So what I would argue, again, we're doing the best that we can. And so if you are borrowing scaling relations or you're borrowing diagnostics from these papers, do it. We are really trying to deliver on our promise. But remember that there are still caveats. And especially if you're interested in studying metallicity scaling relations, you're interested in the scatter, for example, strong line calibrations are always going to cause problems. So what can we do instead? So you'll notice we didn't have a Cecilia plot there. And that's because we really don't think that's the way forward. And so what we're doing instead is trying to develop new tools to leverage all of the information we have to deliver the best possible constraints, not only on metallicity and abundance patterns, but other properties of the nebular gas and massive stars. And we do this through flexible photoionization modeling that accounts for other things that we know about the nebula, the gas density, or it can marginalize over things like the uncertainty in the shape of the ionizing spectra. There's a lot of uncertainty about the ionizing spectra of low metallicity massive stars. And this all comes from Ija Lee's work. Ija is a postdoc at Sierra working with me, who built a neural net emulator for Cloudy that essentially allows you to rapidly sample a parameter space while not taking any shortcuts on the physics in the actual photoionization modeling. And so here what I'm showing is sort of a typical Redshift 2 galaxy, not actually from Cecilia, just from a run-of-your-mill sample with the predictions from Q in orange and the observation in blue. And when you see what this corresponds to in terms of the posterior, you see we're getting pretty decent, still, large uncertainties, but we are able to constrain these properties simultaneously. And what Q, the name of this code, does is, rather than assuming an input ionizing spectrum, it allows you to model the input ionizing spectrum as a 4-part piecewise power law. And so if you have a harder ionizing source than massive stars, or maybe you have a composite object where you're seeing emission from AGN and the sort of star-forming regions, Q is able to handle that basically in stride. It's how it was designed. But we wanted to stress test it in terms of measuring metallicity. So Natalie's been working on comparing direct method metallicities and photoionization model metallicities from Q with one another in order to understand which lines are most important, which lines do you not care about, right? So getting a full spectrum from the near UV to the near infrared at equal depth, that's going to be really hard for large samples. But if you know which lines you need, you can definitely be more efficient. And what Natalie's finding is, so what we're seeing here is the difference between the sort of best oxygen abundance and the oxygen abundance when you use a decreasing number of emission lines in the modeling. And if you only use the strongest lines, you're always biased low. But add just a handful more lines and you shoot right back up to the metallicity that it should be. And so what this is helping us understand is that we thought maybe we were done at Redshift 2, but actually there's still a little more work to do, because a couple of these lines are in the near infrared, which is inaccessible from the ground. So there's a lot of return on investment to be made by doing relatively modest JWST observations that would basically open up a whole new avenue for analyzing these thousands of galaxies where we have observations from the ground. Right, so we improve it by adding only a handful of lines to the things that we already have. There is a caveat though. Remember that high redshift galaxies are alpha enhanced and may have, ubiquitous subsolar sulfur to oxygen and argon to oxygen. And so if you include the sulfur and argon lines in a code that doesn't account for non-solar abundance ratios, you always get your oxygen abundance pegged low, right? Because it was basically a constant sulfur to oxygen and argon to oxygen. now we have basically a constant band of photoionization model oxygen abundance because those sulfur and argon lines are dragging the fit down relative to what we know is true. But if you exclude them, you actually start to recover, again, the properties that we have determined using the direct method. So this, our goal here, by all of these comparisons, is going to be to help provide people the guidance for what they need to do in order to make the best possible measurements. Okay, last topic in terms of abundances is something that kind of came for free. You have to put filler galaxies on masks when you do multi-object observations. Well, we put a few narrowband selected Lyman alpha emitters on the Cecilia mass. We have 30-hour spectra of these really low mass galaxies. So this is a 2D spectrum of one of our typical Cecilia galaxies, and this is work being led by Manelis. This is what you get when you have the faint low mass galaxy. So notice now we're taking a step backwards to where we were with the more massive galaxies prior to JWST. But prior to JWST, we couldn't even hope to do this. So I'm pretty happy. And what we're finding when we vet these and apply, careful methods of analyzing their overall enrichment is that some of these are really quite low metallicity. This is like a several percent solar. But importantly, if you were to extrapolate the high mass metallicity relation, so this is the same sample, basically the parent sample for Cecilia, it's a lot shallower than what we're seeing. And if you do a whole bunch of statistical tests, it's basically, this is robust. This isn't a fluke. This is a steeper mass metallicity slope at low masses than you would have gotten by any draw from this population. Which means that just like we were looking at before, it seems that the efficiency of feedback as a function of stellar mass may be changing. And for whatever reason, these galaxies do not appear to be retaining as much of their metals as we might naively expect it. Little wrench, however. So at Coffee, I talked about an analysis that a postdoc and I have been working on to try and put the Milky Way and Gaia Enceladus, the last major merger of the Milky Way, onto redshift 2 to 3 mass metallicity relations. They fall there. And in fact, this was a main conclusion of our paper, that it fell on the extrapolation of the higher mass metallicity relation. So maybe the picture isn't so clear. My gut tells me that actually what we're finding, some of this is probably systematics. It's actually really hard to put the Milky Way and GSC in this space on the same scale. But also, we expect there to be increasing scatter at the low mass end of the mass metallicity relation. And it's possible that high star formation rate objects might be at lower metallicities at fixed stellar mass. So I think what we need to do with Webb is continue to push down to this dwarf regime at redshift 2, where we can analyze Milky Way progenitor analogs and really get at the what's causing this. Yes?
et al. Paper with the calibration that you're highlighting in this
Yep.
figure. Those points, at what redshift do you happen to know that they're at?
The Nakajima calibration, and this is going to go against what I said, is actually a low redshift extreme analog sample, but it doesn't really matter. If we use other calibrations, or we use Q, the flexible photoionization modeling result, or a couple of these are actually in our TE sample as well, this result doesn't go away.
But why should you expect that the lines should be the same for the local universe at redshift 2?
No. So the calibration is based off redshift 0 galaxies, but the orange points are redshift 2 to 3. These are all the same redshift, actually all the same selection criteria, everything's the same. Yeah.
Except the Milky Way.
Except the Milky Way. We did not select the Milky Way. It is not actually that actively star forming. Okay, I'm kind of running out of time, and I want to show you a couple of other things. So before I close this off, I just want to come back to this like dichotomy that I set up at the beginning. And I said, we want to study things in detail. We want to connect them across cosmic time. I think I've definitely shown that we're making a lot of progress studying individual galaxies in detail. And I think we're beginning to find ways of using these abundance patterns to connect galaxies across cosmic time, or at least motivate the fact that we need to do a better job pushing to the regime where we actually have detailed measurements in the local universe, right? All of the galaxies in Cecilia, the higher mass galaxies in Cecilia, are going to be way more massive than the kinds of resolved stellar populations that you typically see. And so this is really why, in addition to environment, I think dwarfs at cosmic noon are the other big use case for Webb in the next several years. Okay. All of these spectra are integrated light, which means that everything that's in a slit is going into the spectrum. We have very little spatial information about variations in the emission. But we know from looking at nearby systems or resolved systems at higher redshifts or lens systems that galaxies are a lot more complicated. And one thing that I just want to highlight is this concept of what's called diffuse ionized gas. This is ionized gas that exists outside of H2 regions. So it's not associated with star formation. It has some other ionizing source. And what you can see here is an example of a very nearby face-on spiral. This is a map of H alpha. So this is essentially a map of the H2 regions. And here, so dark is where there's more sulfur 2, this low ionization line, relative to H alpha. And it's like opposite. So there's a lot of this ionized gas in this galaxy coming from outside of H2 regions. There are two things this is interesting for. One, if you were to take a spectrum of the whole galaxy, this sulfur line you would just assume was maybe coming from the H2 regions. You would model it as if it was. And then you would get the wrong answer because it's not coming from the H2 regions. Second, thinking about the internal architecture of galaxies is really important. We don't want to know just about star formation histories and whether it's bursty, but we also want to know whether massive stars are forming in more densely clustered environments or less densely clustered environments, and what other things might be happening, right? So the hard ionizing photons that are producing the diffuse ionized gas may be coming from hot evolved low mass stars, and being able to constrain the contribution from those stellar populations at high redshift would be super, super cool. So we've turned to Q again. And this is work being led by Caroline von Reesfeld, a graduate student at Northwestern, and Audrey Clarendon, an undergraduate at Northwestern. And what we've done is say, okay, we're going to exclude all of the low ionization lines from our modeling. We're only going to model the lines that we're pretty confident overlap with with the H2 region. And then we look at the predicted low ionization line flux relative to what we've measured and ask, well, how much of it must be coming from outside of the H2 regions as a way of quantifying the contribution from this diffuse ionized gas. And so what you see here, the green is a sanity check. So doubly ionized oxygen should always be coming from the H2 region. So the fact that the percent coming outside of H2 regions is 0 is good. And then if we look at the amount of neutral oxygen, we haven't done sulfur yet because of that sulfur to oxygen issue. You see that 55% of the oxygen 1 in these galaxies is coming from outside of the H2 regions, which was actually very surprising. The amount of diffuse ionized gas in galaxies is thought to go down significantly with increasing specific star formation rate. And these galaxies have pretty high specific star formation rate. So now we want to know what is potentially ionizing this gas, and that requires us to continue to do this deconvolution. So this is work that's just kind of in nascent stages, but I think is really exciting.
This is at redshift 2?
Yep. Okay, I know I'm very close, but very last thing, I promise. This is a 720 object hour stack. This was our first Cecilia paper because we didn't trust very much about the individual galaxy flux calibration. But what you're seeing here is basically all of the lines that we were used to seeing at redshift 2 are cut off. And now you're seeing 24 lines from 8 different ions across this range, including things that had never before been seen outside the local universe. And I just boxed this line of neutral oxygen, but there's no brackets. So for those of you who are not ISM aficionados, this means it's a permitted line. It's a recombination line of oxygen. Well, no, it's a permitted line of oxygen. If it were a recombination line only, we could use it to measure metallicity directly. You would just count the same way that you count recombination lines of hydrogen. But in fact, it's being pumped by another mechanism. And we can learn this by careful comparison with local H2 regions where this has been studied extensively. And the reason for the excess emission here, the pumping mechanisms could be a variety of things. So basically what I mean pumping is you're exciting higher energy levels. It's not just being ionized, recombining and cascading down, right? So you're pumping but not ionizing. Could be Lyman beta fluorescence, direct excitation by starlight. It's really hard to tell if you only have one line because you can't compare the different branching ratios. But this lensed object at redshift 2.3, Godzilla, they have the same line for this individual source and all of these other lines from ground-based spectra. And two advantages: this is lens, so it's extremely bright. Two, it's a single star-forming region, essentially. So none of this other concern about whatever else might be contributing. We're just looking at one extreme star-forming region. And after careful comparison with our observations and theoretical predictions, what they suggest is that this is actually a non-erupting high redshift luminous blue variable, basically an Eta Carina that's not currently exploding. Oops. Okay, I'm happy to talk more about this afterwards. But what I want to point out is, to date, this line has, so it's been observed in lens object and one other individual galaxy. This was a paper by Mirko Kurti a few weeks ago. We see it in basically a third to a half of all Cecilia spectra. We see this line. Now we see it, and it appears to be weaker relative to H alpha than it is in Godzilla, which means that we're probably only seeing it from a fraction of the star-forming regions in the galaxy. But that comparison, having that anchor point for a single star-forming region, and having the amount that we're observing in Cecilia galaxies, could help us understand how many stars or how many star-forming regions have some event like this going on at a given time. So I'm really excited about this. You can't understand high redshift galaxies without understanding massive stars, so I'm always delighted when we see something that might help us move forward.
Can you just put all that in context in the Milky Way? Why doesn't it show this at all?
Yeah. So basically, these are going to be really dense star-forming regions where you have these globules of gas that have, what you're seeing is the oxygen emission from only near those dense, oh God, what are they called? Weigelt blobs. And so this is not something that's happening for every massive star in every star-forming region. But we do expect that star formation is more highly clustered, like denser, higher mass, like more massive stars maybe in high redshift galaxies for a variety of other reasons, signatures of chemical enrichment and other probes of density. And so I think it's not perhaps surprising that you would see a difference at high redshift. The other challenge is a lot of these lines are in the near infrared, so they're not, and they're weak, so they're hard to observe in like very large samples of local H2 regions, but we do see it in Orion, for example. So well-studied H2 regions, we've seen examples of this.
So just to understand, this recognition to be forming like in a molecular file.
So the exact geometric configuration, I'm not sure that our observations are saying much about.
But I guess the question is just in the Milky Way.
I'm not familiar with a ton of other examples beyond Orion.
Thanks.
Yeah.
But you referred to an LBB, that's Carina.
Yep, that
You
Eta
see
Carina.
it in Carina.
Yep.
As a whole, not just looking at the LBB.
Well, we do, like the spatial distribution of that emission at Eta Carina. I'm not actually sure. Anyway, I will leave you with my apparently out of order conclusions. And thank you for your attention. Oh, I had intended to end a little earlier.
So thank you for your wonderful talk. I was wondering, are you seeing any trends in the like dig fraction as a function of mass or metallicity and how does that compare to like the local universe expectations?
That's a really good question. Caroline has literally just got the machinery working, so we do not know the answer to that question yet.
Yeah, so about the second point, so I think you did show the position of the Milky Way on that plot. So I'm sorry if I missed it, but is it ever possible for you to like unwind the clock and basically put I guess like try to figure out the abundance of the Milky Way progenitor like at redshift 2 to 3 and see whether where it will.
That's what the blue points represented.
Okay.
It's
So
that was the so that's where our attempt to rewind it. That's the points from the paper I showed earlier today.
Okay.
Yeah. In my best attempt to put it on this scale. But yeah, I mean the samples of well-studied low-mass galaxies at these redshifts is still actually relatively small, surprisingly, and some of them are subject to selection and observational biases that I think make them not terribly representative. Not that, of course, the Milky Way is representative. It's the Milky Way. It's one object.
The O1 brackets being partly diffuse.
Yeah. Good stuff.
Yeah, that's produced right at the very edge of H2 regions.
Yes, it can be.
Classical ones.
Yep.
Charge exchanges.
Mm-hmm.
The culprit there. It makes me wonder whether maybe real H2 regions aren't ideal H2 regions.
I mean, that's,
and they have
yes.
corrugated edges.
Yep.
And so on. Maybe this is an artifact of that.
Yes, I think actually that's a really good point as well. So we unfortunately don't have the spatial resolution. So when people look for this in, say, manga, they're looking at it and seeing that it is spatially not coincident. It's not at all near star formation. We don't have that. But your point is a good one in the sense that potentially by comparing this with as analogous a sample as possible in the local universe, we might be able to say something, not necessarily with ISM structure, but maybe something about the H2 region stratification, which is something we're looking at with density and temperature as well. I just didn't have time to talk about it.
So from looking at the Milky Way, like a lot of the ionizing flux produced by O stars are not captured in H2 regions, constellation regions. There's a very diffuse, low density extended regions.
Yeah.
Which is a perfect way to produce this stuff.
Yes.
Even in the Milky Way.
Right. So again, this is where the limitations of our high redshift sample really become apparent. In low redshift galaxies where you can isolate the spaxels, you can see by photoionization model analysis that the ionizing spectrum should be harder than photon leakage from H2 regions. Like it can't explain it all. But we unfortunately, again, without the spatial resolution, can't say that. So I think, the interpretation of this is going to be more complicated, and perhaps like we shouldn't be talking about it as outside of star forming regions, but rather outside of ionized hydrogen, or like outside of the part of it that has H2. Yeah. But I think it was really interesting to me because we'd seen some of these mismatches in line ratio diagrams that had always puzzled me. And I think this is one of the only, I'm just really satisfied that we're beginning to quantify it. But a lot of work left to do on the interpretation for sure. Both of you, yeah.
This was a very interesting talk. I'm going to give a couple of minutes for the online people to chip in case they want to. But if there are not any more questions, I suggest we should just go upstairs, which is behind, and we can Allison, another round of applause.
Thank you for asking so much. You look deep in thought.
What's that?
I said you look deep in thought.
I'm thinking about the lithium cyanide gas.
Yeah.
Well, I mean, there's no one in the Milky Way for 40 years. Okay, but what you're saying though is there are too many hard photons at large distances.
That's what the manga people say.
That's what the manga
I've not tried to look at it myself. I think doing something like Q, which is so agnostic to the ionizing source, could be potentially interesting. I think what we're going to need to do actually, I mean, and who asked the other question? I don't know everyone.
Peter.
Yeah. What's his
Yes,
last
Peter Martin.
Okay. Both were, I think, assigned that really we need to go back.